Hey everybody, it's Mrs. C. I am coming to you today with a quick clarification video. I don't know if I've ever done a clarification video, but it needs to be said. I would like to just clarify the world's most confusing definition. Here it is. The world's most confusing definition is the answer to the question, what is a function? Now we're beginning linear algebra, right? And one of the things I'm asking you to do is do a little bit of vocabulary work. And one of the words, of course, we always want to define when we do linear algebra is a function. So you Google it, and you get many times, or you look in the back of a math book, say, and you get the world's most confusing definition. And it's in my opinion, I know I'm not the only one, but this is my opinion. The definition of a function is that for every x value, there is only one y value. Now, that seems like maybe the world's most simple the world's most simple definition, but it has confused more people than it has actually, cleared up the confusion for. And so it's such a simple one. For every x value, there is only one y value. Now, as a math person, I get this definition and it's very clear to me. But before I was a math person, it confused the heck out of me, and I'm going to explain why. But first, let's just discuss what is a function. Okay, so a function has many faces, and I talk about it with my students, the many faces of a function. You can be given a graph, say y is equal to 2x plus 3, or a line, I should say. And though it looks like an equation, most of us that know more about the x and y's is we know that we can graph this on a coordinate plane, right? And so knowing that we can graph this line on a coordinate plane, maybe it'll look something like that. Maybe straighter, but it'll look something like that. We call that line a function. Now, there's other things that we can do. We can take a nice little table of data, say, give it an x, y pair, and we have a domain. Say that my domain is a 1, 2, and 3, and I can utilize that table of values to create a relation of data. So if we did that real quick, if x value was 1, right, 2 times 1 is 2 plus 3 is 5. And if the x value was 2, right? We've done this in other videos, so if I'm confusing you, please go find my intuition on domain and range and all that fun stuff. But 2 times 2 is 4 plus 3 is 7. And then if we did it one more time, we're evaluating our x value, we're given our domain of 3, and we do 2 times 3 is 6 plus 3 is 9. Okay, so there's a nice little set of data that we could plot. And if I had, plotted well enough over here, we would probably find that those points fall along this line, ish, because I kind of freestyled that line. But yeah, so those points can be found on that line in different places. Now, sometimes we'll express our domain and range not as a graph, that would be one face, right? But we can express it as a table, and we can also state the relation. So what is the relation of this function? Well, given the table, I can see that this specific relation was a 1, 5. It was a 2, 7. And it was a 3, 9. It's just the collection of the points that were within that set of data here in this table. Okay, I could ask you, could you state the domain of that relation? Well, if I looked at this line, I would tell you that the domain was infinite, because it appears like there's arrows on the ends of those, the little line segment, right? I got arrows, which means I don't have a line segment, I have a line, and my domain would go infinitely, and my range would go infinitely. But if I didn't have those arrows, I would have a finite or a specific domain and range. But given, first of all, this table only, so if you look only at the table that I drew, we could clearly state that the domain is 1, 2, and 3, because those are my, x values, and that's my domain. My range is 5, 7, and 9. Those are my range values in the table that I was given that was a finite, a specific set of data. And so I could express that data in a relation that would look like that. Now, why all of this, talk about domains and range and relation? Well, they have a significant impact on this question of what is a function. So if you remember the definition of a function, for every x value, there is only one y value. What that definition is telling me is it's really specifically, I think, talking about this table of values. So let's go over here and look at a nice clear table of values. If I give you the xy and I do the, what were my numbers? Let's go 1, 2, 3. 1, 2, 3. Then I had y values of 5, 7, and 9. Now, for every y value, I had only one y answer. And so if you look from here to here, I have a 1 and a 5, a 2 and a 7, and a 3 and a 9. So what would it look? This is a function because I can clearly see for every x value, I have a distinct and only one y value. So what exactly would a non-function look like? Well, a non-function or a line or a set of data that was not a function, I call it a non-function. I don't even know if a non-function is a word, but it's not a function, right? What would not a function look like? Well, a function that is not a function would look like this. 1, 5, 2, 7, 3, 9, and 1, negative 5. Oh, hang on a minute there. Wait a minute. There's two x values here. And so with the two x values, meaning I only had the value of 1 in the domain, right? There's a 1 here, and there's a 1 here. That's the same 1, right? Well, when I put in a 1, I got two different y values, and that's what they're talking about. They're saying that if you have two different y values for the exact same input, that is not a function. And I'll tell you right now what that gets confused with, and you might even see it because you might already be in that same confusion, is it gets confused with something that looks like this. 1, 2, 3, 4, 5, and then maybe 5, 7, 9, 5, 2. Now note here, I have two of the same y values, and I find that when you look at the definition, x value, for every x value, there is only one y value. This is where the confusion is because you hear one y value. That's all you hear. And look over here. This has two y values. And so students mistakenly say that this is the graph of the line that is not a function when it is actually this one. Now that you understand the confusion, and you probably thought you got it until I said that, we would take a look at what a function looks like, and then I think you'll understand more than anything, how do you identify them. So a function can have a lot of looks. It can be a straight line like that, but can also, should have drawn a whole bunch of these little guys. Hang on, change of plans. No, not change of plans. Just let me make them a little smaller. Okay. So we have a lot of coordinate planes, right? I'll just put a bunch of them. It isn't the prettiest one I've ever done, but it'll do. A function can look like this. Straight line, going like that. And it can go in any direction you want. A function can go across, straight across like a horizontal line. They don't have to be straight. They can curve. They can curve like this. They can curve like that. They can curve like this. They can do all kinds of really cool curvy. Watch it. Watch it. Woo! They can curve all over the place. So you might be asking, well, if they can do all that and they can still be a function, these are functions. Funks. Then what? Wow, that looks a little bit inappropriate. Functions. Much better. Then what the heck does a not a function look like? What does it look like if you're not a function? Well, let me show you. To be not a function. To not be a function. Sorry. To not be a function, you have to do a couple different things. No, not a couple different things. You only have to do one thing. Let me see if you can figure out what it is. Okay, I got my coordinate planes. Here we go. Here is an example of not a function. I will give you another one. I will give you another one. I will give you another one. And another one. And another one. Okay. These are different than these. Now, what do these have in common? These have curvy lines, and these have curvy lines. So we can't say, oh, you're not a function if your line is curvy, because that's not true. These are functions, curvy lines. You could also say, well, then it must be if you have only maybe, if you have too many curves. Well, no, this one has a whole bunch of curves, and it's a function. This one has a whole bunch of curves, and it's not a function. So let me show you straight out what's the difference. I'll go back here. I'm going to get myself a nice black line. To identify quickly a function versus not a function, you take what we call the vertical line test, and you draw yourself a vertical line straight through the center of your graph. And you ask yourself, did I hit that line more than one time? And in the case of this, no. You can draw that line in another place on that same graph. Did I hit that line more than once? No. Come over here. Did I hit it more than once? No. Did I hit it more than once? No. More than once? No. More than once? No. More than once? No. How about now? No. How about now? No. Now? No. Now? Still no. 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 Now, I'm looking at the way I drew this one, and I actually drew it to look like a function. So sorry, that was my freestyling. This one we'll get into. I'm just going to erase you just a little bit. You're behaving a little bit too much like somebody who's not a function. There we go. So no matter where I do that now, it's still a no. I'm only hitting it once. All no's. So these guys hold up to the vertical line test. I draw a vertical line anywhere on the graph, and I can't hit it more than once. Look here. Well, this would be a big, yeah, because it's a vertical line, right? Well, it's supposed to be. I freehanded it. What about this one? Oh, I hit twice. I hit twice there. I hit twice. I hit twice. These guys are not passing the vertical line test. What about this one? Oh my gosh, I hit a bunch of times. Now look at this. I only hit that graph over towards the back end of what looks like the S one time. But the deal is you only have to fail the vertical line test once in order to be declassified as a function. So it's okay over here. That's great that you're a function over there. But, excuse me, you just hit 3 times. You're not a function. And that, kids, is the only thing that you have to understand about functions, is they have to hold up to the vertical line test. These guys are not functions. They just failed all over the place, right? What does that look like? when you're actually looking at a table of data. Well, I want you to take a look first at just a quick little sketch. Oh gosh, okay, I'm sorry. Try that again. Okay, so I've sketched a very standard, typical non-function. It's a curving line, but the way it curves this way, rather than opening up, it is definitely not a function. And I've thrown down a couple numbers just so that we can throw some numbers down on our table. If I take a look at a couple points, some important points, right here, for example, I have a point right here. And let's say, for example, that point is at 510, because that's what it appears to be, right? And then let's take this point that looks like it falls right about there, and we'll say that that point appears to be 5 negative 10. And then maybe we'll pick this point. That's an easy one to get. I didn't really put that value, but let's just say for the case of argument, that's maybe negative 7. And so that would be, what would be 0, negative 7. So let's just do that. 3 points. Awesome. Good. Now, the ones that we want to talk about are, of course, the ones that would have failed the vertical line test. So we can throw that 0, negative 7, and then we'll throw the 5, 10, and then we'll throw the 5, negative 10. Okay. If I do my vertical line test right here, can't you see that you're hitting in the exact same place? And the value that we're hitting is at the 5 here. I hit 5 one time and I get a 10. I hit 5 again and I get a negative 10. And that's what it's talking when it tells you that you can only have one y value for every distinct x value. Meaning that if you're going to have two different y values for the same x, you do not have a function. And so what we're looking at is in a table of values, you will look to where you have x represented 2 times, and it gives you 2 different outputs. Now, on a map, it's really obvious, because on a map, you would be given something that looks like this, say 1, 2, 3, and say 4, 5, 6. And I'm using different data, but you would maybe see that the 1 connects to the 4, maybe the 2 connects to the 4 also. The 3 connects to the 5, and then the 3 connects to the 6. Now, the reason this is not a function is not because of the first set of lines. Let's write that. In that table, it's always easier, I think, to look at it as a table sometimes. I have the values of a 1 going with a 4. I have a 2 going with a 4. I have a 3 going with a 5. I have a 3 going with a 6. It's here where I have the same value in my domain getting 2 different y values. Same input, but giving me 2 different outputs. That is not a function. Now, if you chart or graph all of your data, you can always just do a vertical line test and understand that you're going to have a vertical line anytime you have the same x value, because you're going to be hovering over each other at 2 different places on the y. Trust me, the definition way more confusing than the actual application of it. So hope this didn't confuse you more. I hope this cleared it up so that you know what you're looking for to decide if a function is or isn't a function. And just to recap, if you have the same x values, and for those x values you have different y's, that is not a function. See you on the flip side.